Okay. The 2n dimensional space in which we will consider the evolution to take place. Suppose if you have a system with n degrees of freedom, you require n coordinates and the corresponding n momenta. Then the space in which the evolution will take place is called the phase space. If you consider only the coordinates, they form a space called configuration space, and only the momenta, if you consider, they form a space momentum space. And the solution curve to the equations which we will come across, they describe what is called a phase trajectory or the solution curves, right. This is the terminology. The solutions traversed by representative points are follow the solutions of the equation. We will now first write down Hamilton's equations and then later connect it with physical systems such as Newton's laws and so on and so forth. Okay, abstractly first we will write down and then we will see the interpretation, how they are relating various things. So, we will start with a column vector. These are coordinates and the corresponding momenta. Equations are of that form. Ith coordinate qi, its time evolution depends upon, I called it I or L, I, okay. dH by dpi, and evolution of pi dot is minus dH by qi. Okay. I can rewrite these equations in a compact form. How? I make a column vector of q's and p's. Gradient of h is a vector.
This p and q, they are conjugate variables.
They are conjugate variables, exactly. dH by, so you consider a 2n dimensional column vector starting with dH by dq1 ending up to dH by dpn. First all the q's, then all the p's. This is the gradient of the function h. H is a function of z and t. So, the equations take the form, the equations above, they can be rewritten compactly as z dot equal to j gradient h. Okay. All those equations, all those 2n equations can be written in this compact form. That is why we choose this notation. Okay. If the Hamiltonian, that function h whose derivatives we are using, if that is time independent, then the differential equation is autonomous, and then we will later see that on every integral curve, on every solution curve, the value of h is preserved, and therefore we call that system to be a conservative system. Now let us come, how does it, huh? Okay. If see this equation, no, these equations in general depend upon t, but suppose if I consider a Hamiltonian that is independent of t, then the equations are autonomous. Non-autonomous will have t dependence, autonomous do not have explicit t dependence for the vector field. This right hand side is the Hamiltonian vector field j gradient h. Okay. So, now having written down the equations without any motivation, just in abstract form, let us connect them with something that everyone knows. Okay. So, relation with Newton's law, Newton's second law, which is written here, mx double dot is minus gradient of v, where v is a potential from which I derive the force. I now set p equal to mx dot. This is definition. Okay. P has been defined as mx dot. Notice that P as well as x dot, they are vectors. Okay. And write Hp to be P square upon 2m plus V. If you write it in this form and work out the equations, they will exactly be satisfying Hamilton's equations. So, this is the connection between Newton's law and Hamilton's equation. Okay? Look at the individual equations. Xi dot is Pi by m. This is consistent with what we defined here. And Pi dot is minus dV by dx. So, that is consistent with Newton's second law, because this is the rate of change of momentum that is equal to the force. This is how they follow. And notice here I have taken energy as the Hamiltonian. So, for mechanical systems, this is the rule. If you consider Hamiltonian, it is normally the total energy. That is the rule for mechanical systems.
In the original Hamiltonian equations, was there a negative sign already?
Yes, yes.
There was.
I will just show you. There is a negative sign in the second equation. That is why that matrix J captures the essence. Okay. Now having, no, did I miss something? No. Now let us consider some simple examples. This AICTE brochure you sent me says discuss free particles, harmonic oscillators and so on. So, that is why these examples. Okay.
But this is really good, because this is probably not derived in this formalism in any of the textbooks. So, it's good that it's
There are huge number of books.
okay.
Yeah.
Okay. But it will form the notes then. Thank you.
Yeah, this is more, as I said, it is a capsule. So, you just swallow it.
Yeah.
Okay. Now, free particle. Free particle means what? That either V is taken 0 or some constant. I have taken it 0 for simplicity, but it can be a constant. Okay. In that case, the Hamilton's equations, they will read xi dot is Pi by m, and the second equation is Pi dot equal to 0. Now, that second equation you can immediately integrate, because Pi dot is 0. So, Pi must be a constant. So, if Pi is constant, then velocities are constant, because we have defined P to be proportional to x dot. Mx dot was defined to be P. So, therefore, velocities are constant, and xi's, how do they change? Look at the first equation, xi dot is Pi by m. Pi is constant, therefore, right hand side is constant. As a result, xi dot is a constant, and therefore, xi evolves linearly at a constant rate, at a fixed rate. So, that is how,
Assuming that P is equal to 0, x is 0.
yeah, that assumption I have already made, but that is not, that is without loss of generality. If I had not chosen the initial time to be 0, but had chosen something else, all you have to do is to replace t by t minus t0. So, instead of x of t, you will write x of t minus t0. Okay. This is without loss of generality, I have taken it. In some crazy systems, you cannot do it. If the system is highly nonlinear, you cannot arbitrarily shift them like this. But I am dealing with linear systems at the moment, so that there is no loss of generality in that. The second example is a harmonic oscillator. In fact, this is the reason when I chose how to write a second order differential equation in terms of first order, I had purposely chosen this equation, so that my job now becomes a little simpler job. This is the equation, and with omega square equal to Km, I consider rescaled, I consider scaled variables, so that P is defined as not just mx dot but x dot by omega. And then go back and consider this Hamiltonian, which is the total energy, and as I remarked earlier, for mechanical systems total energy is the Hamiltonian. So take this Hamiltonian, then Hamilton's equations reduce to very simple form. X dot turns out to be omega into P, P dot turns out to be minus omega x. Okay. That is simply substituting in the equations. Okay. Now, I am putting it in the form of a two-dimensional matrix equation, that is the top line. dz by dt is az, where z is xp column and the matrix A, left hand bracket of A has gone to the top line, does not matter. This is 0 omega minus omega 0. Look at the equation. This is the equation. Okay. That is why that matrix reads like this. Now you will notice that the matrix is nothing but omega times j. Okay. And now I can simply solve this equation. We have already seen how to solve a linear homogeneous autonomous equation. The solution is exponential of AT acting on the initial condition. So that is this solution, exponential AT acting on the initial. Now the only question remains, how do I calculate exponential of AT? That is now in this case very simple. In general, there is an algorithm to calculate exponential of a matrix, but let us not worry about it, because in this case it is very simple. I have already written down some properties of J, right? J square is minus 1, minus identity. J cube will therefore become minus J, fourth power will become plus identity, and so on. So you will see alternate terms, they keep changing signs. Okay. Now moreover, it turns out that series that we had written for exponential is actually absolutely convergent. So I can rearrange them. I can club all the order terms and all the even order terms. Alternate terms I can club. And that will exactly lead to this. Okay. Why? Because you are, let us write down first 2-3 terms, it will become obvious. Exponential of omega, what is it, omega j into t. So let us club omega t, which are numbers, and j is a matrix. Okay. 0th order term is identity. First order term is j times omega t. Second order is j square, which is negative of identity, minus omega square t square upon 2 factorial. The next order term is j cube, which is minus j omega cube t cube upon 3 factorial, and so on. Now you consider this term, then the fourth order term, and so on and so forth. That gives you a cosine. You can, there was a fact, no, that is fine. This term, third order term, and so on and so forth. Pull out a factor of j and it will give you sine. As a result, you get this solution. Okay. Now, you will easily realize that the solution curves are parameterized circles. Cosines and sines, they give you circles. Now, why did I get circles? Because I have chosen scaled variables. If I did not choose scaled velocity, if I had kept original form, if I had written p equal to mx dot and not scaled it with omega, I would have got ellipses instead of circles. That is the only difference. So, this is the second example. Now, this is more general form in n dimensions with a non-autonomous right hand side. There is a vector field depending on time. Maybe I will skip it at the moment. If time permits, later I will come back to it. But there is nothing much in this. Okay. All that you have to realize in this this M is a square symmetric square matrix. This is a bilinear form. This is all that you have to realize. Otherwise, things are very straightforward. Again, something of importance. This is not a linear system. Okay. Central force field. How does it is simple to work out the central force field problem. If instead of considering Cartesian coordinates, you go to polar coordinates. So, introduce x equal to r sin theta cos phi, y equal to r sin theta sin phi, and z equal to r cos theta, and then rewrite those equations where Pr is mr dot, P theta is mr square. Oh, there is a dot missing here, please correct. P phi is mr square phi dot sin square theta. There is a dot missing here, please.
Dot square by
No, mr square into theta dot.
r theta phi.
Yeah, the polar coordinates, spherical polar coordinates. Now, notice that if you use them and write the Hamiltonian, kinetic energy plus potential energy, that is the total energy, you will notice that this is independent of phi. If it is independent of phi, that will naturally mean that if you write the equation for P phi, it will lead to a constant. Okay. And here are very important examples of such a V. The Kepler problem, in which potential is minus gmm by r, where m and m are masses of sun and earth. In the case of hydrogen atom, the potential is minus e square upon 4 pi epsilon 0 into r. Now, there is a little cheating here. This is not exactly what one does. One reduces the problem to a particle moving around another point, because if you consider, for instance, both proton and electron, proton is very heavy compared with electron, but it also is affected by electron. So, instead of considering that, you consider the motion around a fictitious point, and instead of original mass, you use what is called a reduced mass, which is given by reciprocal of that reduced mass is 1 upon mass of proton plus 1 upon mass of electron. But so that is the bit of cheating I have done in writing those formulae, but because those are the forms you know already. This is how the system is. Now, let us come to another very important construct. Okay. Poisson brackets have many very special properties, some of which I will list later. And before going to the Poisson brackets, let me remark what is an observable in classical mechanics, in Hamiltonian mechanics. Any smooth function of position on phase space is a observable. Okay. So, that is the observable. Why smooth? Because I want to differentiate it, sufficiently differentiable. It doesn't require, one doesn't require infinitely differentiable, just couple of times is enough. So, if there are 3 such functions h, f and g, I define Poisson bracket of f and g to be the gradient of f its transpose, because gradient is a column vector. I want a row vector. So, this is the transpose, that is why that Twitter. Gradient of f, then the matrix J into gradient of G. In a more explicit form, it is df Twitter by dq dg by dp minus df Twitter by dp dg by dq. Here I have written it in the explicit form, or if you want to use it in component form, this is the definition in the component form, but it is very nice to deal with a very compact form. Okay. Now, if f and g are smooth functions, so also will be their gradient vectors. As a result, the right hand side will also be sufficiently nice, and therefore, f and g itself is a smooth function. Okay, this observation is important because any of them can be considered to be a Hamiltonian, and the Poisson bracket eventually can also be considered as a Hamiltonian. We will see if time permits, I will talk about the meaning of that Poisson bracket. Okay, what does it measure? Let us consider some simple properties. Simple properties, first property, it is bilinear. It is linear with respect to both f and g. That means if you replaced f by linear combination of two functions, you will get the corresponding linear combination. Okay. That is built because the simple property of the derivative that we have used, the gradients that we have used. Okay, if in the gradient, if f is replaced by a linear combination of two functions, let us say f1, f2, then the gradient will split into linear combination of two gradients. So, that is the first property. Second, it is skew symmetric. That means, if you interchange f and g, there will be a sign change. See here, look at the second line, there is a sign, negative sign here. So, if you interchange f and g, negative, and exactly, that is why it is skew symmetric. Third line says it satisfies Leibniz's rule. Leibniz's rule is a rule for differentiation of product of two functions, right? Now, the important thing at this stage to realize, and this is what Dirac had realized, that this leads to a process of differentiation in the space of observables. What is a derivative? Derivative requires linearity and it satisfies Leibniz's rule. So, in the space of functions, defined on the phase space, that means functions like f, g, h and so on, which are functions of position on phase space, you have linearity, the first property, and the third property is Leibniz's rule. So, therefore, in the space of observables, you have a derivative, you can define a derivative, and this was what Dirac considered as an important point when he used Poisson brackets to study his quantization procedure. And then from Poisson brackets he went to commutator brackets that these people will tell you about. And the last is a little tedious thing, it satisfies Jacobi identity. Its derivation will take some couple of pages if you work out in detail, but take for granted that this is true. And Jacobi identity together with these other things is interesting because it defines mathematically what is called an algebra. So, that is what algebra together with a Jacobi identity. Okay. So, these are the simple properties which you can verify simply by using the definition, you do not require anything else. Now, how does an equation of motion look like using this? That is the important thing for us. So, if you consider f to be a function and H to be the Hamiltonian. It can explicitly depend on time, so that you get the partial derivative with respect to time. When you consider total derivative of f, it will depend on this, and it will depend on the variables that label f. So, I take the derivatives. For instance, if I consider f, I forget t at the moment, okay, because it's taken care by the first term. Okay, so let us focus on this. Then I have to take the derivative of this. So, I take derivative of f with respect to q, and then derivative of q with respect to t, which is q dot. Similarly, when I take derivative of f with respect to p, I will get df by dp into p dot. Now, for q dot and p dot, I use Hamilton's equations, and that is how you get this bracket. That is how you get this bracket. Okay? It is as simple as this. Now, you will notice, since this is a skew symmetric, this bracket being skew symmetric, bracket of h with itself will vanish. As a result, the derivative of h, the total derivative, is simply the partial derivative. What happened? Something went wrong.
Screen sharing stopped.
Just, can you? No, I can't see even the.
I'll set it.
Okay. But let us talk in the meanwhile. I told you some time back that continue on the board. Okay, thanks. Now, there are some very interesting things to note. If you take Qi and Qj, their Poisson bracket turns out to be 0. Look at the definition. This straightway follows from the definition. Similarly, if you take two P's, the bracket turns out to be 0. If you take Qi and Pj, their bracket is 0 unless I equal to j. And if it is I equal to j, then it turns out to be identity. Now, these are the properties that are used when you go to quantum mechanics for writing the commutation rules. And of course, trivially, as I mentioned earlier while writing here, h, its bracket with itself being 0, if there is no time dependence, this will itself be an integral of motion. What is an integral of motion? Integral of motion is a function that is constant on a solution curve. It may have different values on different solution curves. It is not a constant. It is a constant only on one curve, on only one solution curve. Okay. Let us come to this important result. When I talk about statistical mechanics in the next lecture, I will make a reference to this. What does it say? It says, firstly, we will talk about areas in phase space, and later we will talk about the densities defined on those areas. So, what does this result say is the following. Suppose this is the phase space, and here I consider a closed surface and some volume inside it. Okay? And then consider the evolution of the system under Hamilton's equations. Obviously, each of the points here, they are not going to remain there. With time evolution, they will map somewhere else. and this shape may become different. It may look different, but I remarked earlier that if the solution is unique, it will not happen that two trajectories cross each other. They will not intersect. Okay. And this leads to the conclusion that this boundary will go map onto another boundary. Then all the interior points, they will remain interior. They will not, there won't be any mixing of them. Interesting thing that this theorem tells you, that shape may change, but the volume contained here will be exactly the same as the volume of that modified shape. That is important, and this is going to be important when we talk about statistical mechanics later in the next lecture. So how does, well, there is an intuitive proof, but it will take a little time, which I won't give you. You can see that intuitive proof worked out in Percival and Richards. Okay. What it is a proof that works only in 2 dimensions, but that can be made exact in 2 dimensions. Here is a proof that will work in all dimensions. Yeah.
Example घेऊन आम्हाला करता येईल.
Oh, sure. Sure. See, basic idea is the following. For that intuitive proof, I will tell you the basic idea. Suppose I can, in 2 dimensions now, so this is one phase curve and this is another phase curve. Suppose these are 2 curves. So if I consider an area here, okay, what will happen is that these points on this line they will be mapped somewhere else. Points on this line, they will be mapped somewhere else. How much will be the distance between them? That is dictated by the gradient. And you can see what is gradient proportional to. This line depends upon J gradient, and this line depends upon the interpretation of what is the gradient. Okay. So what is the gradient? What is the interpretation of gradient? You put in that and put in this, you will see that if this line shrunk, then this line will expand, and so on. Their product will still remain the same. That is the intuitive proof, which can be made rigorous. But here is a proof that is exact. Okay. Suppose we consider a small volume. Once the proof is given for a small volume, you can always convert it to a big volume. Suppose V is the small volume, dq1, dq2 up to dqn are the sides for that. Well, for simplicity, shape is taken to be a parallelepiped. Okay, that's why these sides P1, P2 up to Q1, Q2 up to Qn, dp1, dp2 up to dpn. This is in the neighborhood of some point, let us say Qp. Now suppose the system evolves for time t, a small time dt, suppose if it evolves, then Q will become, Qi will become Qi twiddle equal to Qi plus first order term, Qi dot dt, and I will ignore the higher order terms, because even this term is not going to contribute, so higher order terms will certainly not. Similarly for the p's. Now the changed volume V twiddle is the determinant of the Jacobian matrix into the original volume, and you therefore must calculate the Jacobian matrix. That is that matrix there. So to that order, these are the 4 matrix elements, and you expand it, you will get terms of the order of, so first term will be 1 when you set dt equal to 0, plus terms of the order of dt square. There is no term linear in dt. Since there is no term linear in dt, d by dt of the Jacobian determinant vanishes, and it will mean that volume is preserved. Okay. This is what happens in this case. And this is an important result, that volume in phase space is preserved. In fact, in Hamiltonian dynamics, something much more interesting happens, that there are invariants called the Poincare-Cartan invariants, and this is the lowest order invariant. This is the invariant corresponding to second order, but then there are invariants of all higher orders, okay, fourth order, sixth order, and so on and so forth. All of them are going to be preserved. And in fact, this itself is an important property here and in statistical mechanics. You may wonder that if I have one system, why do I look at so many systems? Okay. Why do I look at so many systems? This tells you their neighborhood properties. Okay. So that is why we look at so many systems. And in statistical mechanics, this is an essential thing. Suppose if rho is a probability density, okay, it is a function like any other function on the phase space. So write down Poisson's equation of motion, it looks like this. Total derivative is partial derivative plus the Poisson bracket. Now suppose if the system has come to an equilibrium, then this d rho by dt will vanish. As a result, partial derivative of rho plus the Poisson bracket of rho with h, that will vanish. Okay. So that is, the right hand side will be 0, and that is how it is used in statistical mechanics. Okay. Can I take 15 more minutes? I think so.
Yeah, yes.
Okay.
Yeah.
So I will just talk about some ideas that are important. The detailed proofs I may not give. Okay. And then maybe if time permits, I will come to the meaning of Poisson bracket. What does it measure? Okay. So first is time translations. Okay. So consider evolution of an observable, let us say f, and with time independent Hamiltonian. I am now considering hereafter only time independent Hamiltonians. So that the equation of motion reduces to df by dt equal to fh, just the Poisson bracket, no explicit time dependence, partial derivative being 0. So now what is the meaning of this equation? Applying the Poisson bracket with h, which is the Hamiltonian, dictates that the observable flow translates over time. So the right hand side is the Poisson bracket, and it decides how f changes with time. So if I consider a infinitesimal time step, then that equation guarantees the time translation. And of course, once you know for some small step, if nothing goes wrong, you can integrate. And this is where the proof is required. I will not give you. Okay, you can see the detailed proofs elsewhere. Another simple thing is about linear Hamiltonian systems. I did not have time to talk about canonical transformations, the transformations which preserve the geometric structure of the phase space and Hamilton's equations of motion. What I will do is, instead of that, I will consider linear Hamiltonian systems and demonstrate everything in that, because that is what is simple. And the machinery for that we have already written down. Okay. So a linear Hamiltonian system is a system of 2n ordinary differential equations. Again, z dot is j into gradient of h. Okay, where Hamiltonian has to be quadratic. Why? Because otherwise the equation will not be linear. Gradient has to be linear. So therefore Hamiltonian at most can be quadratic, nothing more. So this is the quadratic Hamiltonian. 1/2 for simplicity of writing the equations. It's not crucial, but it simplifies the eventual equations. Then Z transpose, because Z is a column vector, I want to make a row vector. So Z transpose a matrix S, square matrix into Z, where S can always be taken to be a symmetric matrix, because there are Z's on both sides. If it is not symmetric, you can always readjust it and make it symmetric. So S is therefore a symmetric matrix. Now use this H and write down Hamilton's equations. What is Hamilton's equation? Z dot is J grade H. So use this form and calculate. It is J times S acting on Z. That is as simple as that. So this is linear now in Z. Let us call the matrix J into S to be some matrix A, which is a square matrix. That is this matrix. And in terms of that, this is the equation. This is now a linear differential equation. That is why it is called a linear Hamiltonian. Okay. Maybe I will come to it later after finishing this topic which I have opened. Okay, I will come to that. So let this discussion be over and then I will come to it. In fact, its detailed proof requires what is called Hamilton-Jacobi equation, which I am not introducing. But what can be argued with the help of what I have introduced, I will explain. So now linear equation can always be integrated. We have seen how to integrate that. You compute exponential of AT, act by that on the initial condition and you have the solution. So that the term is on the right hand side, that is the explicit form. Now notice that the matrix A, which is defined as J times S, has this nice property. Okay, because of the properties of J, it turns out that A transpose J plus JA is 0. This is the proof. I have written it in the bracket. A tilde is the tilde of that definition. S being symmetric, I have not written S tilde. And instead of J, if you consider J tilde, it is minus J. So that is the reason. So that A tilde J turns out to be S and JA turns out to be minus S. So they cancel and this is the property. In the linear context, this matrix A is called a Hamiltonian matrix. And if you consider the operator O to be defined by exponential of AT, then it is simple to verify these properties. O transpose J, O is J. Matrices satisfying this are called either symplectic matrices or linear canonical transformations. The idea is that if you use such matrices which satisfy this property, they preserve the form of Hamilton's equations after changing the coordinates. So if original coordinates are say Q and P, we called it Z. So if original coordinates are Z, and if I operate by O and on this end, suppose I call that Z tilde, and write down equations for this instead of this, and I have this property of O, which is O transpose J, O is J, then the form of Hamilton's equation is preserved. Okay. That is why they are called linear canonical transformations. Now, since we did not have time to discuss canonical transformations, this is a good enough example you can take for linear systems. And now, I will come to the question you had asked for in this particular case about time evolutions, time translations. In this case, the time evolution by O can be seen to be unfolding of canonical transformations. So, successive unfolding of canonical transformations is what gives the time evolution in this case. In fact, this observation is useful in other contexts. When you wish to integrate Hamilton's equations of motion numerically, instead of Runge-Kutta or anything like that, you devise an algorithm based on what is called canonical transformations, because they are guaranteed to preserve the structure. They are called symplectic integration procedures. So, instead of Runge-Kutta, use symplectic integrators, and they have this property because they being symplectic or linear canonical transformation, they preserve the structure. So, after numerical integrations, you do not lose the, because of the errors, you do not lose the Hamiltonian properties of the system. Now, let me come to your question and then I will talk about something else. Oh, what happened? Yeah. Look at that equation. df by dt is the Poisson bracket fh. Okay. If I take a small time step, how would I expect f to change? I would expect f to change, that will become df by dt into dt in a small time step. That is equivalent to the Poisson bracket fh into dt, right? So, what does it mean in the infinitesimal time step dt? H has generated the effect of whatever translation happens to f. H is controlling that effect. If you take a different H, you will get a different evolution. So, what is that time translation is therefore dictated by this. Now, the more rigorous proof of this I will not give. This is the intuitive proof, but more rigorous proof either uses this idea in detail and whatever I said is made rigorous, or else go to what is called Hamilton-Jacobi equation and then consider the time evolution. Okay. That is the thing. Now, let me, in the last few minutes, let me talk about the, what does it Poisson bracket measure? Suppose this is the phase space, okay, and I consider the functions f and g. I start with some initial point. First, I consider f to be the Hamiltonian, okay, and then consider the time evolution. Suppose I come from here to here. Then I consider g, and then from that point, let us say this for time t1, and then from that point, I consider now the Hamiltonian to be g, and then evolve for time t2. This is first Hamiltonian f and this is Hamiltonian g, according to that. I will come at some point. Instead, if I started here and first evolved according to g for time t2, I may come here, and then according to f for time t1, then from here I may reach somewhere else. Okay. Now, Poisson bracket measures the failure of these two flows to commute. If Poisson bracket is 0, what will happen is that these two endpoints will become the same. If the Poisson bracket is non-zero, these 2 points will not become the same, and the difference between them can be bridged by considering the bracket to be the Hamiltonian and time to be t1 into t2. So, if you bridge that for time t1 t2 and you consider the bracket F and G to be the new Hamiltonian, then you will bridge this gap. So that is the interpretation of what does it have. When you go to quantum mechanics, instead of Poisson brackets, you will have commutators, and commutators precisely measure the failure to commute. Poisson brackets measure failure of these flows to commute. Exactly the same thing happens there. Okay. So that is one additional comment. I will make one more comment and then stop. I had written this equation for O. Where did it go? Here, last paragraph. I had written O transpose J O equal to J. I will write a few more equations and then you will see what is going on. Okay. So let me first write, then explain. A few more equations I have written. You would have seen similarity between these equations. O transpose J O is J. So whatever is sandwiched between O transpose and O has been reproduced on the other side. This is the equation for symplectic transformations. If I consider G to be the Lorentz metric, 1, minus 1, minus 1, minus 1 and zeros all others. And if lambda is a linear, is a Lorentz transformation, it satisfies this relation. If I consider a orthogonal transformation, if T is an orthogonal transformation, it preserves the identity. If U is unitary, and that is what you will come in quantum mechanics, okay, it is a complex vector space in which you are applying unitary transformations, then it preserves the identity. Now, whatever is sandwiched in between is reproduced on the right hand side. What you can show using this property is that all these transformations form a group. Here the group is symplectic group, here the group is the Lorentz group, here the group is what is called orthogonal group, and here the unitary group. Okay, all these groups, they all preserve a bilinear quantity. Here linear Hamiltonian systems gave rise to the bilinear expression for the Hamiltonian, and the inner products were bilinear. So this preserves what is called a symplectic scalar product. This preserves the standard inner product in the Lorentzian framework. This preserves the Euclidean, and here this is the complex. Associated with each of them there is a geometry that is preserved. That gives symplectic geometry, this gives Lorentzian geometry, this gives the Euclidean geometry, okay, and this gives the geometry of, you would see this in fact in Hilbert space when you make unitary transformation, what happens. So this is the commonality of these structures. I think I will stop here. Anything more would have required much more work. So as I told you at the beginning, I am giving a capsule, so swallow it. Okay? Because detailed proofs will require more hard work. Okay. So any questions?
I have a few comments.
Yeah, please.
I mean, few comments for you. There is a much deeper connection that you alluded to between the
commutator bracket being 0 or not being 0.
Yes. And Dirac's observation is more important.
That
That,
and the kind of uncertainty relation that we talk about.
yes.
So how does it connect with Poisson bracket the way you showed the difference and the commutator brackets not being 0 or not non-zero?
That you require Campbell equation. So if you are exponentiating, if you are exponentiating, then Hausdorff-Campbell formula you have to use. Any questions? Any comments? Okay, so let us stop. I hope there are no questions means either nothing was clear or everything was clear. Huh?
There were questions in between.
A few. Okay.
Thank you, sir.
So we'll break for lunch now. I'll check if there's a bus after. Bus is there. So we can break for lunch. Come back by 2 o'clock and continue with Professor Rao. Yes. After 8 was lunch. If we can come back earlier, that's great. Earlier the better. Yeah. So, well, 1:30. Sorry. Yeah,
1:45.
1:45. Okay. So let's plan that.
पाऊस शेतीला लागेल.
छत्र नाही
नाही सर थोडं पळत जावं लागेल. Actually, if you reverse, there is a gap. And that gap is very similar to they don't come in. Then that gap is the probability the answer. See, the gap comes when you. The gap is zero. The commutator is zero. Corresponding gap won't be there. So you can measure them simultaneously in the other side. If the gap is there, that means they don't commute. And then that is the answer.
Maybe this is
That's the point.
connection.
Right,
Classical.
classical equivalent. So that gap which can be bridged classically, which cannot be bridged quantumically.
No, that leads to
that.
If there is
That is not a
non-zero commutator, what he's saying is
then
that
that
gives rise.
equivalent of that.
You cannot simultaneously diagonalize them.
Correct. Exactly.
Okay. Since you cannot simultaneously diagonalize, you push that.
But you can actually see the commutator.
Maybe what you are saying
So
is
is that
that connection.
your connectors seem to be
Yeah, I'm just saying, see, commutator
You
bracket.
start with a commutative and then
There's a new one.
No, commutator is not zero. Commutator is zero, that means you can simultaneously diagonalize.
Here also, if you also bracket is zero, then there is no gap.
There is flow,
There is because the
flow.
flow comes back to where you are. So that the idea is similar. When you switch over to
So this is
commutator,
like the original.
Oh, yeah, sure.
the bit comes from
This is-
commutator not being zero. That it's embedded there.
Correct.
It's embedded there.
Let's go.
Here, in some sense, it is embedded, but classically it can be corrected, as we know that the exponents can correct.
Proof for that Poisson bracket is in Arduino.
Oh, it's a run.
That how to.
So that's a very beautiful point. Unknown.
Why people don't use combined dynamics?
They do use.
I mean, we all saw Lagrange.
No.
Where? It's a question of where you, where it is used.
Yes. Lagrangian because she follows from variational things.
Yes. We do like a very.
that is, for example,
Secondly, for conserved quantities, Noether's theorem is
Is a
automatic
very
in
powerful.
that.
Yes, yes.
Whereas in Hamilton's case, there is an analog of Noether's theorem. In fact, there are other symmetries which are not present in the Hamiltonian. But you don't come across them.
Also, the classical fields,
Ah.
to go through the Lagrangian.
Correct.
Not
No,
through the
because quantization is difficult.
Ah.
And Feynman's prescription is more useful there.
You always go through Lagrangian, you take the infinite degrees of freedom, then quantize it.
Yes.
That's the straightforward route for quantization.
So,
Second,
there-
I mean, field.
Lagrangian becomes, then you calculate exponential of action.
The action also.
That is like calculating if you turn the go from this Lorentz metric to Euclidean method, then it becomes like calculating the exponential of minus beta h in the statistical mechanics. That is what people know already. So partition function.
But
So partition function is analogous to in the lowest order.
in the lowest.
Higher order you don't know. मी आता घरी जाणार आहे.
Walkable distance is fine, पण मध्ये पाणी खूप साचलं.
घरी येत
So
सर्व.
it's better to take.
जेवण घरी घरी तिकडेच घरी घरी.
पाणी
सर्व घरी गोंधळ असतो.
हा, ते तुझे shoes ओले होते.
मी त्याला सकाळी सांगितलं की मी घरी येईन.
गाडी आहे. He was asking, is it walkable? Is it
डिस्टन्स
distance?
परवा मी येणार नाही तर उद्या नाही आहे मला काही परवाही काही नाही शुक्रवारी आणलंच समथिंग
I think it should be fine.
So, you will let me know when the next lecture is.
Yes, yes.
Then I will come
हो
आता तुम्ही आहात ना दुपारी?
नसेल तर मी नाही
ओके. मग मी ईमेल करू
शाळांना सुट्टी मिळाली.
घरी येत. ओके.
त्यामुळे हे
Right.
better to go home.
Yeah. मग मी ईमेल करू का तुम्हाला? I'll
Well,
email.
August was
हो हो. चालेल. I'll tell you in advance. Yeah. Yeah.
Sir. हात फक्त खडू लागला आहे. Ah, no, no.
Okay.
आज तर शाळांना सुट्टी मिळाली ना.
Okay,
त्यामुळे
yes.
तर घरी
Next
भाग आहे.
generation is at home.
Okay. So there is someone to look after one of them. But the others, they will be creating a huge noise.
भैया येत नाही का तू?
येतो नाही.
Professor Zog has given his book, which we have taken in, and Srirang has ingested it into the LMS. So that's available as notes as well.
The book is not available at the moment.
No, not the book. Condensed notes from the book are available.
Oh my. It's there. So, good afternoon, everybody. Huh?
आहे का चालू माईक ते त्याच्यावरती कॉलर इथे कॉलरमध्ये जावं बटनाला
Huh. So, I mean, I'm supposed to give you some idea on quantum computing as such. But in the spirit of what is being done, some background quantum mechanics, which is at the contact with this quantum computing, I'll start developing that. So let me start with the basic measurement properties of classical particles. Suppose we have a classical particle, and then you have if you make measurements, first thing is that its dynamics is given by the forces acting on it, and in order to find out its state, first you have to measure it at some t equal to 0, and then as an initial value problem, you have to solve the equation of motion, if possible. Then that will give you the state at the time of that system. So measurement is fundamental. Measurement is something you cannot avoid. And therefore, let us find out the basic characteristic of this classical measurement. And that is if you measure some quantity, say x, okay, on a particle or on any classical system under identical conditions, the values that come out and measurement results are not exactly the same. They are distributed over a short, depending on the accuracy of the measurement, they are distributed over a short range, and they are distributed on both sides of the average value, and that average value is the value that you take to be the value of that particular observable pertaining to the classical system. And this probability distribution over these values around the average value of x is normal. It's a Gaussian distribution. The reason is you have, these basic physical reason is you have the apparatus that you use to measure it is made of enormous number of atoms and tiny particles which jostle around, vibrate around their equilibrium position, and each vibration is independent of each other. So mathematically, it becomes the random variable that up to whatever very large n is very large, and each is identically distributed. So your basic variable is the addition of identically distributed random variable, and there is a central limit theorem that says that when this situation occurs, then this x is distributed as a bell shape, random. The Gaussian distribution. So the basic thing that pertains to this is that we take this x average value of x to be the value, and any value of x which lies in this short range is doesn't is not another value of this quantity. So this value is the value of that particular variable x, and it's independent of the method of measurement, and it is as if it is the property of that particular system, and what measurement is doing is just revealing the value. So measurement doesn't change this particular value in any way, and so the value before measurement and after measurement remains the same. It doesn't change. Okay. So if I the first tenet is if I repeat the measurements of the under identical conditions, you get this particular kind of distribution, and the average value of x is the value. And it is independent of how you measure it, and whether in fact independent of whether you measure it or not, because this particular value is pertaining to that classical system, and measurement just reveals it at a particular time. Of course, this value can change with time due to its interaction with this environment, but that's another thing. So it may depend on time. So it depends on what time you make the measurement, or at what time this particular value pertains to that particular classical system. Okay. So what you can I mean how do I specify the state of the system? State of a classical system? Just the list of all measurable physical properties possessed or by the system at a given time. So the next observation that we make is that means that all possible measurable physical properties have definite values at any given time in that particular system, and you can measure them as accurately as you want. That is, suppose depending on the kind of application I am doing, I need a particular accuracy. Then in principle I can get accuracy. There is absolutely no problem. There is no fundamental limit on getting the accuracy of the value pertaining to the system at any time. By I mean if a particular method is not giving that accuracy, we assume that you can such a method and obtain that. Okay. So this is the main characteristic of the measurement of made on the classical system. Now this means let us take a particular case. This means that let me take the two fundamental quantities, position, okay, and momentum of this of a classical particle. So by the definition of specifying the state of the system, it means that these two quantities have specific values, definite values with the system, and they can be just measured by different methods or same method, whatever it is. So there is absolutely no problem. And this is very important because classically all other quantities like say angular momentum or energy are all functions of these kinds of fundamental observations. So the fact that you have the position and momentum have classical, precise values at all times is lies the foundation of the classical physics. Now the question arises. Now suppose I mean, let us find the consequence of this particular fact. So suppose position and momentum are available, precisely available, whatever accuracy we want, they are available. Then I mean, you or if you want this the particle is here. So I this is the position vector. So if at some t naught or some t particle is at this particular point, then I know the momentum. So that means I know the velocity. So I can find out the next position after time. Batteries are on. Hello. Yeah. I kept it. Hello. Okay. So suppose now I assume that I know x and position and moment precisely what position I want are known, and the position of the particle is at a particular point. Then its position after some time, say I call it delta t if you want, I can find out as x plus x dot into delta t, and I can choose delta t as small as I want. So that just means that the particle is moving on a continuous path, and at any point your velocity vector or the momentum vector is, as was pointed out in the previous lecture, is tangent to that particular path. So the knowledge of precise values of position and momentum are imply a continuous and differentiable path of the particle. Now suppose you are given that the particle is moving on such a path, continuous path. Then you can find out its derivative. I mean, there is no problem. Suppose x is this is the position given by at a particular time t, and you know that differentiable. Then you know that x dot exists. The next position is x dot plus delta t. So it is if and only that if you know the values of position and momentum precisely, it means it is on a continuous path. And if you know that it is on a continuous differentiable path, you precisely know the position and moment. Okay. Is it clear up to now? There is no problem. So now the question is, let us take the case of a quantum particle. The question is whether the quantum particle has a differentiable and continuous path. Now this is a fundamental question, and you have to answer it by performing an experiment, because you cannot answer it offhand like that. This is a fundamental problem about quantum particle. So this is the corresponding experiment is a famous experiment. The double slit experiment, which was discussed before, but we will discuss it in a slightly different perspective. This much is enough. So there is a source, whatever which is emitting electrons. So suppose typically two successive electrons are emitted in the interval of 10 raised to minus 3 seconds. Okay. And at 50 kilovolts, for example, you have the average velocity is 10 raised to 8 meters per second. So what is the distance between two successive electrons? It is the distance traveled by the first electron, just up to the moment the second electron is emitted in this interval. So that is 10 raised to 5 meters. Or 10 raised to 3. Am I making some mistake? So the 10 raised to meters per second and 10 raised to minus 3. So that is 10 raised to 5. That is kilometers. 1,000 kilometers. So that means if I make this arrangement, then there is no more than one electron at any in the apparatus. So we want to perform this experiment, ensuring that at most one particle is present within the apparatus at any given time, and this is the way you can do it. Okay. So 50 kV is the source voltage. Electron emitting source. Electron source. Okay. Yes. At 50 kV, the average velocity speed you will find it 10 raised to 8 meters per second. That is right. 100 10 raised to 5 kilo is 100 kilometers. Sorry. 10 raised to 5 is 100 kilometers. Sorry. 100 kilometers. Sorry. The factor of 10. Okay. So that means this will ensure that there is only one particle always at the most one particle at any given moment. Okay. So this is important. This is how we perform this experiment. Now what are the results? What is experiment? What happens is suppose I look at only individual electron passes through this particular structure and impinges on detecting. So it is like a lump. It's like a particular event, particle event. But then when we send say large number of electrons, say 100,000 or something like that, then and look at the cumulative effect, then we will clearly see the presence of dark and bright fringes. Now this is a kind of interference pattern, and we know that this is a basic characteristic of the interfering waves. So this is a wave characteristic. Okay. So now these waves, I mean for any kind of interference, we need two sources. Okay. That's two sources, two coherent sources, emitting signal. Then you will get the interference and the corresponding result. So this is important. So how do I get these two sources? I have only one particle at a time. I have only one particle at a time in the apparatus, and I have two slits. And still I am getting interference pattern. So that means I must have two sources. These two slits are acting as two sources. Okay. What does it mean in turn? It means that my electron has to pass simultaneously through both the slits. Extremely weird, but this has to be done. This must happen. Otherwise, you won't get any interference pattern. Okay. Another thing that you can experimentally see. How do I see it experimentally? I close S1. Then what happens? Interference pattern is lost, and I get a bump with a peak in front of S2. Now this means from this observation I conclude that the electron must be passing through S1 because if it was not passing through S1, okay, then it have made any difference. If the electron was not passing through S1, then closing S1 should not make any difference in the observed interference pattern. But it is making a drastic difference. Totally interference pattern is lost, and I get a bump. And exactly the same. If I close S2 and S1 is open, then I get a bump in front of S1. That's it. Interference pattern is again lost. So this is here. I mean that means electron was traveling through both S1 and S2 because closing one drastically changing the result. Okay. So that means that our question is answered. What was our question? The question is whether a quantum particle has a differentiable smooth path. The answer is no. A quantum particle doesn't have a differentiable path. Okay. And therefore, I mean, but we know that if it doesn't have a differentiable path, we already found out that this means that the position and momentum of the particle cannot be simultaneously measured, cannot have precise values at the same time. Because if they had precise values at the same time, I could show that it is moving on a path, on a differentiable path. Okay. So okay. So let us now go a little deeper and so let us use what has been told in previous said in sort of taught to you in previous lectures that the state of a quantum particle, electron here is given by a wave function like this. And since we are dealing with now waves, let me call it say A e raised to I kx. And so what is superposition? Superposition summation of A k is I. I mean, so I want I also not very nice. So I can say N e raised to I k n x. So this is your superposition. So how does this psi relate to your observation, the interference pattern? Okay. So I mean this is I want to make it depending on this. So this is the thing. Okay. So how does this connect to the observed pattern? So this observed pattern is basically the intensity of the number of particles hitting on the screen. So on the bright bands, the density of particles hitting is increasing, and on the dark bands, the density of particles is of zero. For example, at the point of the dark band, we assume that there are no particles or almost negligible particles hitting there. So what I have to do is I have to relate my psi to this particular observation, the profile of particles. So we know that, I mean, this can be done in the following way, that suppose I have this is the dark band, this is whatever. So I get a point, say at some point x on the screen, okay, and then I find out the number of particles hitting there, and then I divide, suppose it is nx, and I divide it by the total number of particles hitting on the screen. Then what does it? What will it show you? What is this? This is just the probability. This is the empirical way of finding out the probability of particles hitting at that particular place. Okay. So this must be my mod psi x dx. Because from the fundamental tenet of quantum mechanics, as you have already learned from previous lectures, that this is the probability. Okay. So this is the way you can actually empirically find out the value of this distribution of mod psi x squared. Okay. So now let me just consult this mathematics. Let me work out. So let me at t equal to 0, I write x at t equal to 0 equal to a exponential I k x, because this is t is equal to 0. So at the origin, that is when x equal to 0, my psi 0 is equal to a. Now I want to find out. Now from this I want to find out what is the wavelength of this pattern. So I want to find out the distance lambda such that psi lambda equal to a. For this to be true, I must have exponential I k lambda equal to 1. That is right. So or k equal to or lambda equal to k upon 2 pi by lambda. K equal to 2 pi by lambda. Because this will happen only when this k lambda is 2 pi. So k lambda is 2 pi, that means lambda equal to 2 pi by lambda. K equal to 2 pi by lambda. Similarly, I want okay. So at psi 0 at t equal to 0, what will happen? Psi 0 equal to a again. Now I want psi 0 t equal to a. That is right. Okay. Or exponential minus I omega t e raised to minus I omega t equal to 1. That's omega equal to 2 pi by t. So I can write this as psi equal to a exponential 2 pi I into bracket x by lambda minus t by t. So let me write this superposition. So yes, just a moment. Psi p. I want to find out the intensity at p. So psi p equal to, or the amplitude at p. So psi p is equal to psi 1 plus psi 2, where psi 1 is equal to a1 exponential 2 pi I x1 by lambda. This is x1. x1 by lambda minus t by t, and psi 2 is equal to a2 exponential 2 pi I x2 by lambda, here x2 minus t by t. Yeah, somebody was saying something. No, omega t has to be 2 pi. This product must be 2 pi. Yeah. Okay. Now, you require t such that, I mean, this equation is satisfied. But you can take it capital T, it doesn't matter. I want to find out t for which this equation is satisfied. So that's it. So when I suppose, when I substitute these expressions in this particular equation, when I add them up and simplify, I'll state the result. The result is psi at b, or in fact psi at p mod square is dx is equal to psi star p psi p. This product I have to evaluate, and these expressions for psi, so psi p, I'll have to write psi p. So this psi p, this is the psi p. So I'm taking this psi p here, and this is the product that I will have to evaluate. And the result is a1 square plus a2 square plus twice. You can find out for yourself cos of 2 pi. So a1 square is the intensity or the probability of reaching that particular point P when S1 is open and S2 is closed. A2 square is the probability of reaching point P when the reverse thing happens, that is S2 is open and S1 is closed, and this term gives you the interference effect. As I change x2 and x1, as I move P along this particular detecting screen, x1, x2 minus x1 will change, and cos is a periodic function, so it will give you interference pattern. Yeah. So we obtain this particular thing, but there is, as he has rightly pointed out, what we are finally interested is to match this particular expression with the observed pattern. This formula must exactly produce the observed pattern. So where is the gap? The gap is at lambda, as we have just pointed out. Now what could be this lambda should be dependent on? What are the free parameters here? What can I adjust here? I can adjust the source. I mean emission of it. That's the only thing that I can adjust. Everything else I cannot do anything. That means I am adjusting the momentum. I increase that kV or decrease it. The speed with which these electrons are moving, getting emitted, is changed. That means the momentum is changed. So this lambda must be determined by the momentum of the incoming electrons. And this relation was first given by de Broglie, de Broglie or something like that. See, a famous Pula Deshpande, this humorist, Marathi humorist, Pula Deshpande, once said that if you write Gajendra Gadkar, its French pronunciation could be Joshi. So, I mean, and de Broglie, I say it's de Broglie. So this fellow give you this formula. And why we believe in this formula? Because if I use this formula in this expression, I reproduce exactly the observed pattern. No problem. So this validates this formula. Now we can, I will not go into details, but from photoelectric effect we already seen the Einstein equation. These two equations, they are quite simple, but they cannot be justified or make even plausible using any kind of classical applications. They are completely outside of classical world. Okay? And they form the foundations of, at least one of the foundations of this quantum physics. Okay. Now let us recollect what we have learned out of all this. Why did we do this? Okay, let me consult this. Now, yeah, there is one.
You also started off with the flux being 10 raised to minus 3 per second or something.
No. Yeah. That is the distance and the time between successive emissions. I am assuming that simultaneous emissions are not there. 2, 3, 4 electrons simultaneously emitted. That's not there.
But even if it was there, all of this will still hold.
The point there is, my crucial assumption in all this is that there has to be a single electron at any time. Now, if I allow many electrons to be emitted, then you have a classical explanation for that. When you have a beam of electrons, then you can produce this interference as no problem. The crucial thing is there is only one electron, one.
That is why we have.
That is the problem. That is the point. Yeah. It's a single electron.
Practically, is it possible to emit one electron at a time?
Yeah. That's what I told you. So I have a source which is emitting successive electrons at a time interval of plus to minus 3 seconds. And the speed of the electron is 10 to 8 meters per second. That means the distance between two successive electrons is 100 kilometers. So the equipment is much closer than that. So no problem. Okay. So what have you learned? The first and foremost and most important thing that we have learned out of this is quantum superposition. Quantum superposition. Now let me see. Suppose psi1 x is the state of the electron when I close psi2. S2. Okay. Psi2 is the psi2x is the state of the electron when I close S1. When both slits are open, the state of the electron is psi1 plus psi2. So that means psi of x is equal to psi1 of x, or some. I think actually there is a normalization constant. So this is the state. This is when both are open. When both are open, this is the state. This is the state. Psi1 plus Psi2. When one thing is closed, then there is no superposition. Either it is in Psi1 or Psi2. When both are open, we get a superposition. And the interference pattern is the result of this superposition. When the superposition is lost, the interference pattern is lost. When the superposition is on, then the interference pattern is on. So this is the instance of quantum interference, and quantum interference is a result of superposition. Okay. So this is the first thing. And now let me generalize. We learned it in the context of this experiment, but this is generally true. I mean, a general state of a quantum system can be always expressed as a superposition of various states. So this gives you a mathematical structure. What is the mathematical structure which supports this statement? Linear space. So if I collect all possible states of a quantum system, they form a linear or vector space. Because I can take any elements of that space, that means any possible states of the system, and superpose them, and I will get some other element in that space. And what are the superposition parameters? I mean the coefficients. These are complex numbers. So it's a linear space with scalars. What are the scalars? Complex numbers. This is the generalization I get from this particular experiment, and this has been validated by all experiments. So fine. So what is the next thing that we learn? Yeah. There is one more thing which I want to say about this. See, what I mean. These are the superpositions of functions of psi x and psi 2x, psi1x and psi 2x. And the interpretation of these wave functions is that psi of x mod square dx is the probability of finding the particle between x and x plus dx. On the screen, here it is on the screen. Even if you want to go to 3 dimensions, what you do is you keep on moving the screen. Carry out that experiment for at one position of the detected screen, move it, carry out another thing, you will find out 3 dimensional psi of x. No problem. Okay. So this is the interpretation. Now it turns out that this wave function has all the information that you can extract experimentally about that quantum system. Not only on position. Once you know psi of x, then you can find out the corresponding probability of finding various values for its momentum, probability of finding various values for its angular momentum, probability of finding various values for its energy. Everything is possible. Okay. So this is a very important thing that I am stating about this particular superposition. Friends, superposition is the Atma of quantum computing. Without superposition, there is no quantum computing. Superposition gives you the quantum advantage. This is the basic reason, the basic tenet by which a quantum computer or a quantum computing method will supersede classical computing. How it is done, we will see. So superposition is the most fundamental thing, and we learn it from this particular experiment. So this quantum probability. Another very important thing, and that is quantum probability. What we did, since point is here, my interest was finding out the electron reaching here at some point P. And there were two mutually exclusive alternatives for the electron to come. One is S1, slit S1, the other is slit S2. In order to find it, what did we do? We added the amplitude functions or the wave functions, and then evaluated their mod square, size the superposed function. So what you add is the amplitudes, and then you take the mod square to find out the probability. Okay. Now classically what happens is, suppose you have some result or some event which can be realized by two or more mutually exclusive alternatives. Then how do you find out the probability of that particular result? You must add the probabilities of all the alternatives and not the amplitudes. So you have a quantum probability has its own standing, it has its own implications and its own results. Okay. So this is the fundamental thing that you are changing here. That the way you calculate the probability, the way you find out the probability. The way you find out the probability here is you add amplitude first and then take its mod square. That will give you the probability. While classically in regular probability theory, if a particular event can be realized by 2, 3, 4 more mutually exclusive alternative ways, then you have to find out the net probability of getting that particular event is you should add the probability for each alternative of reaching that result. But that's not true here. Okay. So what is the next thing? Yeah, that we have already covered. Okay, fine. Yeah, I'll give you this example. Why it is so drastically different? Let me take this example. See, you suppose this P is at the center of a dark band. P is at the center of the dark band. That means the probability of an electron getting there is zero. Or close to zero, negligible, zero. Let me take it zero. But now, when I use the alternatives separately, when I use closeness S2, so I have only one alternative. That means electron has to go through S1. Okay? And in that alternative, the probability of reaching at that point is zero. It is that bump. Okay? So it's certainly non-zero. Similarly, the other alternative probability of reaching at that point P is not zero. When I close S1, S2 is open, again there is non-zero probability. So I have two alternatives, each with non-zero probability, which together are producing an event of zero probability. See, when I have, there are two alternatives. When I use one alternative, that means what I am doing, I am closing S2. S1 is open. I am looking at the probability of the electron reaching P which is at the center of the dark band otherwise. But now one is closed, so there is no dark band, nothing. So that electron, what is the probability? There is a non-zero probability of reaching. That will be given by that hump. What probability? I can choose a point at the dark band which has sizable probability of that alternative. Similarly, I close S1, I use other alternative, there is a sizable probability or non-zero cognizable probability of getting there. I open the both slits, that is at the center of the dark band. So the probability is zero. So what I am doing is, so you see how drastically this quantum behavior is so drastically different from classical behavior. Yes.
Usually, first probability plus second probability would be equal to 1.
That's what I'm saying, that classically this happens. This happens exactly. When you have an event which can be realized by two alternative ways, mutually exclusive alternative ways, then the probability of that event is the sum of the probabilities of each alternative. Sum of the probabilities. But now here what I am doing, I am summing the amplitudes. So what is happening here is that I have two alternatives. Each alternative gives a cognizable probability of reaching electron reaching at that point. But when I use both the alternatives, that probability is 0 at the center of the dark band. Okay? No problem. Okay, fine. Yeah. Yeah. No, there is no interference. Interference is lost. When you have one closed, you will get a hump with a peak in front of that open slit. You close that, you get another hump which is with a peak in front of that this thing. So the total thing, if you add up them up, then you will get a curve or the additional curve, by addition, whatever. You won't get any interference. Okay, so let me fine. So now what I can do is this. I close S2 and S1 electron goes through, has to go through S1, and in that particular event I look at it as a measurement of position of the electron on the screen. So that measurement of position of the electron on the screen, what I do is I have this particular state of the electron, and then I will say that when S2 is closed and a particle electron hits at P, I get, or I'll write psi1 P if you want, psi1 P, and I'll call the corresponding value 0. I'm sitting on P only. Okay, my measurement is to find out the electron at P. So I close this, I have S2 open, electron reaches here, the event in which electron is reaching here, I know that this is psi 2p and my eigenvalue, the value is 1. Okay? So it is like my physical quantity that I am measuring. What is the physical quantity? Passing through the slits. That is the thing that I am measuring. Okay? And what is the result? Result is reaching at P, and then I have two definite states. What I can say that if the electron is in psi 1, like this, then it will reach P, and I have, if it reaches P, I'll say I am getting eigenvalue 0. Eigenvalue is in my hand. I can assign eigenvalues the way I want. And if it reaches via S2, I know that state is psi 2, and I will say eigenvalue 1. So there are two things. Then what I am doing a measurement where it can take only one of the two values. So this is classically, if you measure anything, say momentum or any kind of attribute of a particle, okay, then in principle that physical quantity can take any real value. There is no restriction. Momentum can take any real value, position can take any real value. Angular momentum, energy, in principle can take any real. Whether it will click or not, that will depend on that system and forces and all these kinds of things. That's a different thing. But in principle, there is no rule or there is no, law in classical physics by which there is a restriction on various kind of physical quantities taking values. But here we have an example of such a kind of restriction. This is a kind of measurement where it has only two alternatives, two results are possible and two values are possible. Okay. In fact, as far as quantum computing is concerned, we will be dealing with all such quantities having only two values. Okay. So These are called eigenvalues. So let me elaborate on that. So in quantum mechanics, let me generalize from this observation. What is the generalization? Generalization is in quantum mechanics, for a quantum system, the properties that can be observed or that can be measurable attributes of the quantum system are called observables. And each observable has a set of eigenvalues. Eigenvalues are fluid, that depends on the situation. There are situations where you can assign eigenvalues. For example, spin or spin down. If you have electron is half integral spin, it has two states, spin up and spin down along the gradient of the field. So I can say that when it is spin up, I assign +1. When it is spin down, I assign -1. Okay. That is not going to change the physics or the kind of thing that. So, but there may be some situations. In fact, in this situation, if you stick to physics, then it is 1/2 h cross. But then it's cross I forget. And instead of -1/2 and 1/2, they are not convenient. So minus and plus doesn't matter. Okay. Yeah. There are physical situations. There are physical situations which dictate eigenvalue. That's it. No, not. No. Eigenvalues are not normalized. Eigenfunctions, the functions are, the states are not normalized. Yeah. So we'll come to that in a moment. So these two are the basic building blocks of my quantum system. That I have to list the observables, and each observable I must find out the eigenvalues. But that is not the end of the story. For each eigenvalue, there is an eigenstate. I will come to that. This is called Kate. We will come to that. So, okay. And the defining property of these eigenstates is the following: that if the system is one of the eigenstates of an observable, and on that, with that system in that eigenstate of the observable, if I measure that observable, then surely the corresponding eigenvalue will turn up as a result, and the state of the system will not change. It will continue to be in the same state. Okay. So this is the basic definition of an eigenstate. It's through measurement. So this is the situation, and then okay. So let me go over to the next thing. Let us explain this Kate thing. Now, it didn't follow directly from our experimental analysis, but we already said that if you know psi of x, then you know everything. Then you know, I know psi of x, and if I want to find out the probabilities of various values of momentum, then I can use that psi of x to find out that. If I want to find out the various eigenvalues of energy, I can use it to find that. Okay? Like this for that particular quantum system. So that means if you know psi of x, then you know all information that you can extract. Information about the quantum system that you can extract. So then it gives me a freedom. This particular situation gives me a freedom. What freedom do I get? What is so sacred about position? Psi of x is one way of expressing the state of the system. But I could express it as well equivalently by saying phi of p. And Anjali has already told you that these are the Fourier transforms and all that, but that's fine. The equivalent. I can use some function of energy, some h of p, or some psi h E. Something. Same state. Physically state is not changed. I am just expressing it in different functions of different observables. I mean, eigenvalues of different observables. So I have this freedom, and I know I could find out how convert from one representation to other. This is a coordinate representation. You have psi of x. Momentum representation, you have phi of p. Your energy representation, you have some other function of E. Okay? And I can convert them from one to other. So this tells me something more. The following thing, that when you have all these kinds of ways to represent the same state, okay, then it is more convenient to represent a state by some abstract symbol and find out rules or find out ways to go over to different representations from that symbol. And such a symbol is the so-called kit. So a state, this I am putting the dot, I mean you can read anything in this dot. Generally, if you have an eigenstate, then that eigenstate is labeled by the corresponding eigenvalues for eigenvalue. For example, I mean if you have for a spin, for example, you have spin up is represented by plus k plus 1 k minus like this. Now how to ket K-E-T. So bracket. Ket is a symbol which symbolizes the state of the system, quantum system. And there are ways to find out, go over to different representations that we will see in a moment. Now I make a point which is already been mentioned, probably more than once by both Anjali and Dilip, and that is that the actual values of different physical quantities must be real. You can't have a complex number, complex energy or complex these things, momentum or any such kind of thing. So that means. So now, how do I represent or how do I represent the operators? I already seen. We have already seen that all the states of quantum system form a linear space. And for example, I must have a mechanism to find out how the state in a quantum system changes with time in that linear space. Or if I make some kind of operation designed by some kind of operation on that, which we will be doing so many times in quantum computing, how does it change? How this particular operation changes the state? The change in state, how do you account for that? The change in state is accounted by an operator, linear operator. These operators are linear. Quantum mechanics is a completely linear theory. So this is a linear operator. Linear operator means I have a superposition, suppose A on psi, and suppose psi is a superposition, so A on alpha 1, psi 1 plus alpha 2, psi 2. This is superposition, A on psi, but psi is the superposition, so A is on this. That is equal to alpha 1 A on psi 1. This is linearity. Alpha 2 A on psi. Each term. This particular linearity, this operation is also crucial, very crucial for quantum computing. So superposition is crucial and linearity of quantum operations is also crucial. This generates huge parallel computing, this kind of thing. So suppose we have some kind of qubits, we will come to that. Some 100 qubits or whatever, and I have a superposition of this 100 qubits, say, huge. Maximum possible terms in 100 qubit superposition is 2 raised to 100. That is 10 raised to 30. What is the power of 10 for a trillion? How much? Who knows this? What is a trillion? Huh? Nine. 3n is, yeah, 12. Who said 12? Okay, fine. So this is 10 raised to 12. And here, what are the number of terms in this maximum possible terms in this superposition of 100 qubits? 10 raised to 30. So that is 2 raised to 100. 2 raised to 100 means 10 raised to 30. That means 10 raised to 18 trillion. Can you imagine a classical computer with this RAM size? No. Okay. So this is the power of superposition. And the power of linearity is what? Now suppose I want to develop some change from psi to some phi by design. This is what I am doing in quantum computing. Okay. So I have to design certain kind of what is called a unitary operator for it. I operate by unitary operator on psi. That means I am operating by unitary operator on each such term. So this is a huge, unimaginable parallel computing. Huge. Of course, there is a problem here because these kinds of large superpositions are fragile, and that is the reason why you cannot draw a quantum computer out of your shelf and you start using it. That is the reason why quantum computers are not that much powerful. Quantum computers are at the moment not available, but there is a promise that they will be available. I see about 2 years ago or 3 years ago, people were asking questions where quantum computing actually powerful quantum computing, whether it will see the light of the day or not. Now, people are asking how much time now it will take to get that. That is the difference, okay? So, we will not come to that. There are various developments, very encouraging developments, especially at Google and also at I will not actually IBM. The other thing is, I do forget the name, very famous name. Tesla, no. It's the company for producing computers, computational. IBM, MS-DOS, Windows, whose window is? Microsoft. Microsoft is developing this Majorana based this thing, and if they are successful, that will be the end of it almost. All problems will be solved, mostly. That is one thing. And then other thing is at Google, Google has developed a method using this artificial intelligence where the error rate decreases as the size of number of qubits increases. It's amazing, just amazing. The error rate is decreasing as the number of qubits are increasing. So these two developments are basically very, kind of have a promise. And there is of course a lot of effort at IBM. They are also announcing various kinds of things. I think a few hundred qubit quantum computers they have already announced. But those quantum computers are not easily available. I don't think they are selling it free. They are not saying that here is a computer, you pay this much and get it. That is not there. That stage is not there. So this is okay. This is diversion. So okay, fine. So where I was? This is the linearity. So this is the linearity, and then now I was coming. We were at the stage of measurement. So now, as I already told you by in the previous lectures, that the eigenvalues must be. Eigenvalues are the only things that come out of the measurement. If you measure a particular observable, then what all possible results of that measurement are covered by the set of its eigenvalues. Nothing outside this set will come out of it. Okay. This is the main thing. Okay. So, and all these eigenvalues are real because these are the values of a physical quantity like energy, momentum, position, whatever that is there. So I need the operator which embodies the result of measurement, not the action of measurement, but the result of measurement has to have this property that or the operator which represents the observable must have this property that all its eigenvalues must be real, and it must also have another property that all its eigenstates must be orthogonal, but we will come to that. So both these properties are satisfied by Hermitian operators. Hermitian operators have all their eigenvalues real and all their eigenstates orthogonal. We will come to that. Orthogonality will come to that. Okay. So this is another thing. Now let me come to the actual measurement process. So we are interested basically in a observable having only two eigenvalues and two eigenstates. So let me stick to that, and it's easy. So some arbitrary state. This is the measuring apparatus, or this box corresponds to measurement. And there are two eigenvalues and two eigenstates. So for any such observable, I am observing some this observable having only two eigenvalues and two eigenstates on some arbitrary state, which is I am just giving a dot there. Anything, the dot can be replaced by anything, it doesn't matter. Arbitrary state, any state. Then the first thing is the result of such a measurement. In fact, result of any measurement, but I am specializing to two eigenvalues. The result of this measurement is one of its eigenstate and its eigenvalue. So whatever may be the input state, arbitrary state, just after the measurement, it will be, say, suppose these are Ket0 and Ket1 are the two eigenstates of that. Suppose. Then the result will be either, say, +1 is the eigenvalue with Ket0 or -1 is the eigenvalue with Ket1. These are the only two alternatives. Now, suppose I repeat this, I prepare exactly the same state, whatever that state is. I keep on preparing again and again that quantum system in that state, and each time I measure it. Then what could be the result? Whether it will be Ket0 or Ket1 or whatever. The answer is you cannot say, you cannot tell it. It is completely random. Let me tell you what is the meaning of random. Random meaning is this. Then suppose I am repeating it. If I get this result, I write a 0 on the paper. I get this, I write 1. And some few million times I do it. So I get a 1 million length of 0 and 1 string out of this. Now, howsoever I study that string, I will not be able to predict what will be the next digit. That is, what is the result of the next measurement. This is what I call random. The measurement is random in this sense that it's not possible to predict in even remotely, in very distant what is the result of this particular
Based on the previous history.
based on the previous history, because this is a random sequence. What do you mean by random sequence? Random sequence meaning is there is no pattern, there is no structure in that sequence which you can use to. You need such a structure or pattern. Without that you can't do anything. Unless you see some periodicity, you see some kind of structure, some relation between these bits that are occurring in that sequence, then you can use that relation to predict. But if you don't find any such relation, you just can't do anything about it. Okay? So this is basically that will happen. So this is what I mean, that this is completely random. But now, as I already told you, that suppose this input state is say 0. That is eigenstate. Input state is eigenstate 0. Then what will happen is, then it will not be random. Then I am sure to get the same eigenstate out with the same result. In the same way, if the input state itself is other eigenstate, say 1, K1, then I will get this result, 100%. There is no doubt about that. This is in fact the definition of the eigenstate. This definition covers everything. Okay. The eigenstate, you have an eigenstate, and if you make a measurement of the corresponding observable, not any other observable, but the corresponding observable on that eigenstate, then you will get for sure the eigenstate out without any change in it, and the result will be the corresponding eigenvalue. Right? So, okay. So, well, then, okay, let's go back to this arbitrary state. But now I can decide the probability of various results, these two results. How do I do it? Again, repeat the measurement under identical conditions on the same state, and find out, suppose I repeat it n times, and I get n0 times this 0, and n1 times this 1, n0 plus n1 equal to 1. Then the probability, empirically, the probability that I will get a result 0 is n0 upon n, and probability that I will get the result 1 is n1 upon n. So experimentally I can decide the probability. What probability, by what probability I can get what result. And I know, and now let us write formally the definition of a superposition. So suppose I have ket psi, and it is summation of alpha k, summation of k. So k is 0, 1, 2, 3, etc. Then the probability that I will get a result L is mod of alpha L, where alpha L is, sorry, what is happening here? Okay. Alpha L is the coefficient of the Lth term. So the result that you, as a result of measurement, suppose I make a measurement on this, and there are some k equal to 1 to some n or whatever, these are the n eigenvalues. I have this superposition, and I make a measurement on this of the observable whose eigenkets are here. Then the probability with which I will get the Lth eigenvalue, Lth state prepared out of measurement is alpha mod alpha L square, or that is alpha L star. So that means this is the empirical way, this is the experimental way of deciding probability. By this probability mod alpha L square, I mean this probability. Okay? This is the probability that occurs, that I can find out. But now there is one more right. See, I am supposed to have, this is supposed to be the probability. So the probability, the total probability that some result will come up, this is the total probability, must be 1. So I must have summation over k alpha k square so the state which satisfies this condition is called normalized, and this is called is called the norm of psi. So this is norm square, norm of psi square. Yeah. This is a quantum state, and this quantum state is the superposition of the eigenstates of some observable, say A or whatever.
When we say the normality, that is our expected one.
Huh?
All summation.
Are you aware of this? You must be aware of the summation convention, summation sign. Huh? Huh? So see, this means that alpha 0 plus alpha 1 alpha 1 kt 1 plus alpha 2 k2 plus alpha 3 k3, like this.
Last year output is what expected. Normality means output is what.
No. Normality means the probability, total probabilities must add. This is the probability. See, what is the probability that Lth eigenstate will turn? I know that we have already seen that as a result of any measurement, some eigenstate will turn up. Now, what is the probability that Lth eigenstate will turn up? That probability is that coefficient alpha L of the Lth term mod square. No, it's not summation. Probability is mod square of that coefficient. But now I want the total probability to be 1. So I must have mod alpha k square, which is the probability of every result of eigenstate turning up as a result of measurement. So that probability must sum up to 1. I mean, if I have some arbitrary linear combination, this kind of condition is not guaranteed, isn't it? So I am imposing that condition. Okay, so this is called normalized state, and this is the norm. Which? No, it's not orthogonality. I am calling it, this is just the norm. Orthogonality which will involve two states. I will come to that. Okay. So, yeah. So let us come to this. So now we have we call that collection of all possible states of quantum system forms a linear space. So there are two aspects of linear space that I will not formally define a linear space, but I have to define linear independence. So suppose I take out of this linear space formed by the states, I take some states, a set like this. Now this set of states is called linearly independent. If it is not possible to express any one of these states as a superposition of the remaining ones from the same set. So suppose I choose psi 3, then I cannot express psi 3 as a superposition of psi 1. The psi 3 will not come here, all the other things. So psi 4, like this. Any number of sets out of the remaining ones in same set. So if I just, if I force myself to do it, then it just means that all these coefficients are zero. The only way I can write like this, if the set is independent means if I take any state out of that set, And if I am bent upon writing it as a linear superposition, then I have to make all the positions zero. That is the only way I can do it. There is no other way, because it's not possible to write it as a superposition of the remaining states. A set which is not linearly independent is linearly dependent. That is you can now in a linear space of all states, you can construct a set of linearly independent sets in such that any arbitrary state in this space can be written as a superposition of the states from that set. I can find out a set of states which is linearly independent, such that any state from the state space can be expressed as a superposition of the states from that set. Is it clear? Yeah. Huh? Yeah, I will come to that. So, such a set is, he has already told that such a set is called a basis. And in fact, there could be infinite bases. I mean, you can. It's not unique. For example, three-dimensional space. Any three vectors like this forms a basis. Yeah, because I take any vector, I can write it as the linear combination of these three vectors. And suppose I rotate this basis slightly. You get another basis.
Is linearly dependent on
This vector is linearly dependent on these. But these three vectors are linearly independent. See, because if I take a linear combination of these two, for example, I will get a vector in the plane spanned by these two. But the third vector is out of this plane. So it cannot be written as a linear combination of these two. So this is a basis. These are linearly independent and this is a basis. Okay, fine. So and you can have uncountably many bases. Like you just shift it, rotate, do something. Every time I am going to get a new basis. And I will be able to write any vector as a linear combination of that basis. So in the same way, I can get many bases in my space. Now my claim is such a basis, each basis has maximal. That is, it contains the maximum possible number of states, largest possible set of linearly independent set. Okay. Why? It's very simple. Suppose I adjoin some state here. Make it large. Now it's a basis. This much is a basis. So I can write this as a linear combination of the states out of it by the definition of basis. That means this total is linearly dependent. It's not linearly independent. Therefore, basis is a maximal set of linearly independent. I mean, it's a maximal linearly independent set. Another conclusion from this is all bases contain the same number of states. Same number. So this is the concept of basis and the linear independence. So that is enough for us. That we will use this. I mean, a formal theory of linear spaces we don't need. So let's go over to scalar parts. So let me I'll justify this notation. Let me call my state space the space of all possible states of a quantum system H. Then I can associate another space called H star, which I will call Bras space, or actually mathematicians call it dual space. असं लिहितात जनरली साधायचा लिहित नाहीत कारण साधायच इज अ व्हेरी कॉमन सिम्बॉल फॉर हॅमिल्टन. हॅमिल्टन इज व्हेरी इम्पॉर्टंट ऑपरेटर.
Small number for scalar, big
Big for operators. That's it. Okay. And this is the symbol for the space, whole space. This is a star. This is gas space or dual space. How is it defined? You. This is a collection of all linear maps. From H to C. That is C means why C? Because it is a scalar sub C. C is the collection of all complex numbers, complex plane. So that is the collection of all linear maps from a vector or element of H is mapped to some complex number in C. Collect all such maps. They form a linear space themselves. And that is called the brass space or dual space. Now this the map that you create like this is not one to one, but we will see that. But there is another map which is one to one. Okay. So let me write that. An element of the brass space or dual space is bra. Now what is bra stands for? Such a linear map. So this maps say a ket in H to some this is called XY. This is belongs to in. This symbol, do you know this symbol? Yeah, it belongs. Okay, so this bra is a map which maps some ket, say Y, ket Y in H state space to a complex number. X is written as like this XY. Okay. No, this is special notation. We will come to that. Complex notation is anything. This is not a general pointer. No. This is a special. This is a quantum. This is called scalar product under certain condition. So yeah, that is a linear. I mean, Mota C. Therefore, this is a complex number. Okay. Now there is a very beautiful. There is another thing. Any finite dimensional space with scalar product. We'll define that scalar product is a Hilbert space. We'll define a scalar. This is a scalar product under conditions. So I'll state those conditions. That is a scalar. But before that, I want to say something very extremely important. So there is a one-to-one correspondence between H and a star. That is given any. There is a correspondence. You can define a correspondence. You can get a correspondence such that given any ket Y in H, you can find there exists a bra Y in H star, and which is unique. This is called natural correspondence. Natural correspondence. And this plays extremely important role in structuring the basic structure of quantum mechanics. We will see that, especially the operators. So this is called natural correspondence, and this is for I mean for every cat there is a unique bra. For every bra there is a unique cat. Such a one-to-one correspondence can be established. How it can be established is it involves kernel and all this kinds of things. Let's forget. So this is natural. Now suppose this map, this particular destination of the map satisfies following conditions. What are these conditions? First is linearity. That is alpha 1 x. I mean, sorry. This is the first condition. Second condition is this. Star means complex conjugate. And then third is so from this it is clear that x is a real number because if you put y by x then x equal to x star, that means it's a real number. But there is something more. It has to be greater than equal to 0. It has to be a non-negative real. Cannot be negative real. This is an extra condition. Yeah. This is scalar product. So if this map produces this number, but now this map has the property that this number has this property. It follows these three things. Then it is called a scalar product. Of x and y. And now you can read the statement again that finite dimensional linear space with a scalar product is called a Hilbert space. If the space is infinite dimensional, then it is more complications are there, but we will not deal with infinite dimensional vector spaces at all. So it's okay. So I call my state space to be Hilbert space by interchangeably and call it state space or Hilbert space. Same thing. So okay. Now let me define orthogonality. So the way we are doing quantum mechanics is with quantum computation in our view. I mean. So this will lead to quantum computation. The way we are doing quantum mechanics, we are choosing the way which is useful for quantum computation. Well, so two states x and y are orthogonal. If the scalar product vanishes. In fact, this is not new. For example, two vectors. Orthogonal means perpendicular. When they are perpendicular, A dot B is a scalar product. This we know from vector, simple elementary vector.
In terms of electron,
No, electron is a quantum system. Electron is a quantum system. It will have its own Hilbert space. I am talking about any quantum system and the corresponding state space. This will apply to all quantum systems, not only to electron. To atoms have
represent two different qubits state.
No. These are two different states in the that's it. No. Of the same electron. Same electron has many possible states. I collect all of them. They form linear space.
And same combining by
This is a scalar product of two states.
Sir, is it correct that in hydrogen atom electron has many possible?
Yeah, we'll come to
Each
that.
of them is orthogonal like this, is it?
Electrons are not orthogonal. States are orthogonal.
States orthogonal to each other.
Yeah, they are because they follow from a way.
One electron can be in any of the states.
Yeah.
So the state
Orthogonal. Yeah, that reminds me of certain things which is very important. We'll come to. Yeah. So this is the orthogonal. These are the orthogonal. So okay. So what is the importance of orthogonality? Let me come to that. So let me come to that. So consider a state psi. Ck say lambda k. Lambda k are the eigenstates of some operator. Say lambda. Lambda is some operator or the Hermitian operator. Okay. It is all real eigenvalues lambda. These are the eigenstates of this operator, and this is some arbitrary state. I am writing it as a superposition of eigenstates. Up to this, is it clear? Now let me take the scalar product on both sides with respect to some state L. So I'll get L psi equal to summation over k Ck L or I'll write lambda L. I am writing lambda. So lambda L psi summation over k lambda k by lambda k lambda k. K is a running index. It is running over this sum. L is some fixed some singled out fixed eigenstate. I am taking the scalar product of this fixed eigenstate on both sides. So I will get lambda L psi. Scalar product Ck lambda L k. So what can you say about this? I mean they are I mean so I have to okay. No, so let me think how to put this. Yeah, okay. Okay. So let me impose this particular condition that this I mean to start with that let this basis they form a basis and we assume that this is an orthogonal basis. Orthogonal basis means what? Any two states in that basis are orthogonal. Okay. So let me impose it and then I'll come back to it. Yeah. So this is one. So now I take the scalar product. Then what can you say about this? Except L equal to K equal to L. Okay. That is called delta KL. Delta K. So when I get so only one term will survive. K equal to all other terms will be zero. When K is not equal to L, they are orthogonal. When K equal to L, I assume that this is 1. We'll justify all this. Because this is the same condition. In fact, we will prove it. We will prove that if a state the scalar product of a state with itself is 1, then that state is normalized. That will I have given it as a problem in that notes.
Say that's an orthogonal.
No. You see, if you have arbitrary state psi and you say that bracket psi is equal to 1, then psi is normalized. That you have to prove. So I have given that as a problem. So you in that what do you call that? The discussion of the people active learning. You will get it in active learning. Okay. Fine.
Sir, just a quick reminder. Time. Yesterday you reminded us to have to be at this time.
4:45.
It's quarter to 4.
Oh,
Tea time as well.
So when do I do the remaining things? I don't know.
Yes. And Shivsagar also said that need some revision for.
He has two lectures today, but he has taken only one.
It was only one was possible. Actually, 2 lectures were scheduled. Mine.
Tomorrow he will take and I will take. Professor Kanere will not be having the lecture.
Okay.
That's what it is me, because that's what I thought.
Okay.
But the schedule says,
Lecture by lecture I was telling you have to reschedule.
So
He will have a lecture day after on qubits and
No, I'll be introducing all these things, qubits and all this.
okay, I'm fair enough. So I'm still confused. So is it okay that we come at 9:30 tomorrow? Is there anyone who can't come at 9:30? Everyone can come at 9:30. Okay. And
you want to take 2 lectures.
I can take.
Otherwise, whatever remaining problem can. You are going to take one. I can take one and he can continue one.
So tomorrow you want to come and give a lecture?
All 3 lectures are over. 2 bits you are taking care of. I don't have to count on.
okay. So
So we
tomorrow
have one each tomorrow as scheduled by you.
Okay. Right. That's the same sequence.
Whatever remaining non-normal qualitative problem, so you can continue with informal foundational aspects tomorrow.
Okay. Zog sir first, then Shivsagar. He continues.
Then post lunch.
Okay. Is the schedule clear for everyone?
It's 9:30. 9:30
will start here.
So just take the poll whether all people agree with exact.
So
चलो
9:30 बस तिथून नाही 9:30 पोचायला
पोचायचं.
9:30च्या आधी पोचायला 9:00 बस आज आली बस आली आणि टॅक्सी सुद्धा 9:30 पोचायला
नाही द सेम वे उद्या गांगल नाहीये उद्या ना मग हां आपण सेम गांगल किती 8:45 वगैरे पावणे नऊ ते 9च्या दरम्यान म्हणजे जाऊन हिला घेऊन आपल्याला चलता है
आणि so we'll break now. We do want to discuss the lab non-recurrent